Hi! In our last video, we talked about centrifugal pump charts and specifically about this curve, head versus flow. Are you enjoying my videos? Please let me know. We saw that when we install this pump in a pumping system, it's easy to find the operating point. It's right here, where the curves cross. But what if the flow that we found in the operating point is greater than the flow that we need? And what if the head is variable and we want to keep the flow constant? Then we saw that it's a typical case for variable speed pumps. We just have to find the velocities for each head, and there are these equations to help us in our task. We've drawn this parabola, which allowed us to find the Q and H values that we needed for the formulas. We did the same for both cases that we're studying. But we ended this video with one question. Could we do this algebraically instead of using graphics? The answer was yes, and that's what we're gonna see now. Okay, let's assume that this is the operating point that we want. Notice that it's in the system curve. It's easy to find this parabola because we know that it goes through this point. We substitute the values so we can find the value of k, and the parabola equation is this one. Now we know the pump equation. There's a video of this channel showing how to find it. Its link is in the description. If we put these equations together, we'll find this one, which allows us to find the value of Q and, of course, the H value of the crossing point. Now we have the Q1 and H1 values and the Q2 and H2 values that allow us to find the velocity that we need through this equation, or this one, help yourself. We do exactly the same for the other operating point that we want. Let's put on numbers. The figure shows a floating structure in a lake with a pump that must pump 35 cubic meters per second against a height that varies between 20 and 30 meters. We must find the impeller velocities for these two situations. Let's start with the 30-meter scenario. Here is the operating point that we wish, so the parabola must go through it. This is the formula of the parabola. We can find its coefficient because we know that point. We substitute the values, and this is the coefficient. Here is the parabola equation. We must know the point where it crosses the pump equation. Here it is, the pump equation. As we saw, it's easy to find Q at the crossing point using this equation. We substitute the values and find this first value for Q. But it's a negative value, so we don't want it. Aha! This one is better. We'll keep it. Now we calculate the H value using the parabola equation or the pump equation. Help yourself. Of course, the value must be the same. Now we have all the values that we need to find the impeller velocity. We choose one of those formulas, substitute the values, and find n equals 1659 rpm. If we choose the other formula, we find 1664 rpm. It's a very small difference, isn't it? We do it all again for h equals 20 meters. Here's the operating point that we wish, so the parabola must go through it. This is the formula of the parabola. Here is the pump equation. We put them together, solve the resulting equation, and find the values for Q and H at the crossing point. Now we're ready to find the impeller velocity. We find n equals 1479 rpm in both cases. Piece of cake, isn't it? What do you think? Please let me know. Leave your comments. Here are the pump curves for the velocities that we found. But what will be the values of the efficiency power, and the required NPSH at the new operating conditions. That's actually pretty simple, but we'll leave that to the next video. See ya! Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.